Hey guys, so we're on the third video for chapter 8, which is all about energy. And I'm going to do another one of those little diagrams with branches off for energy, just because I think those are helpful. So now we're going to talk about mechanical energy. And basically, what's encompassed in mechanical energy, you know what, let's just write mechanical. Wow, that was really messy. Mechanical, right? Mechanical energy. Okay, so let's do some branches off real quick. We have two types of mechanical energy. We have potential energy, oops, sorry, energy, and we have kinetic energy. Those are our two most common forms of mechanical energy. When you talk about energy, you'll hear those. You'll only hear those really. I mean, there's other things like chemical energy, but that falls under potential energy. So let's define these. Let's just let me just split this down the middle here. Oops. Okay. Now, potential energy is basically the energy that an object holds by virtue of its position. That was strange. I don't know what just happened there. Sorry about that. Oh, I know. It's okay. Sorry about that. Okay, so it's basically position relative to Earth or relative to some fixed point. And potential energy, you look at the word potential, and if something has potential, it means it has the ability to go somewhere. It's not going somewhere yet, but it has the ability to go somewhere or do something. So, has the ability for energy, ability for work. Yeah, it has the ability to do something. And that's basically, it's kind of, you can think of it as stored energy, right? So let's give some examples. I'll give some examples. A spring it's either compressed or decompressed. A spring is an example of potential energy. Another good example is a battery. A rock on a ledge has potential energy. It's sitting up here, and it could fall. It could fall down there and create a lot of kinetic energy. So it has the potential. It has the potential to do work. And then another good example would be food. Food has all this. Let me draw. I don't know. I'll draw a pizza. I don't know why I made it green, but it's okay. So food has all this, all these molecules in here floating around. Okay, and these molecules hold energy in their bonds. Now the energy is not moving anywhere or doing anything until we actually eat it. Until we eat it and it goes into our bodies, and we break it up. Our enzymes break it up, and we take that energy and we turn it from potential to kinetic, and we use it to like play soccer or write a book or do something that requires energy, right? So that's another good example of potential energy there. It was like food. I really like how that's an example of potential energy. Now we'll go over here to kinetic energy. It's basically, if you look at the word kinetic, you think of, I think of kinematics. Kinematics has the same prefix there, kin. And kin kind of means, kin, I think, I haven't looked it up, but I'm sure from what I know about Greek and Latin roots, it means fire or movement. And fire and movement are often the same, are often in the same definition simply because movement produces heat. So I think kin would be heat or movement or something of that nature. And so we're gonna put movement here. Movement. So it's kind of moving energy. Moving, right? So then that's really all. So it usually follows potential energy, right? Because if we see that with this boulder. It has a lot of potential energy, right? Then it falls, and it starts building kinetic energy, right? Kinetic, because it's moving, and it starts losing its potential energy because it's getting closer and closer to the ground. And it also potential. Let's give some examples. A car moving car. Really anything that moves. A runner. Falling boulder. Yeah, so those all have kinetic energy. Like a race car. I already said car. What am I thinking? So yeah, airplane, anything that's moving has kinetic energy. So now that we have this nice diagram in our brains of potential versus kinetic, we can dive into the more specific equations and whatnot and math that we use to look at to look at potential and kinetic energy. So let's go ahead and clear this page real quick. Okay, so now I'm going to first talk about potential energy. And basically, we talked about stored. It's kind of stored energy. Stored, right? So yeah, you have a nice diagram in your book. You have kind of with a boulder on a ledge. You have kind of the grassy ledge here, right? And there's this boulder. This boulder up top. Try to draw it in the correct color. There's a boulder up top there, and it has 200 joules of, remember, 200 joules of work, but energy is also measured in joules. And it's actually raised a distance of 2 meters, okay? So this has potential energy because it has the potential to do work. Potential to fall, really. Has the potential to start moving. And gravitational potential energy is the term we use. Gravitational is the term we use when something has potential energy because of its height, because it's raised above a certain fixed point. So we wouldn't talk about gravitational potential energy when we're talking about food. So not with food or something of that nature that's not exactly moving. It's this boulder has gravitational potential energy because it has been raised up. Something has done work to it because it's lifted it against gravity. Against gravity, right? When something is lifted against gravity, it gets gravitational potential energy, gravitational PE, okay? So that's really cool. So then now we have an equation for that. We have gravitational potential energy is equal to the weight times the height of an object. So it's kind of long, so I'm going to abbreviate it like they do to PE, potential energy, is equal to mg, and I'll draw it into the color, h, where mg equals weight and h being height, of course. Height. Wow, it's really not, the pen's not cooperating with me today. Height, right? So that makes sense because the heavier something is, you know, the more energy it's going to create, right? When it's falling and when it hits the ground, there's going to be, you know, just larger ramifications. And the higher it is, the farther it's going to fall, and the more it's going to accelerate, right? So it's directly proportional because as either of these go up, so does the potential energy. If it were inversely proportional, it would be mg divided by h or h divided by mg, something of that sort. But it's not, it's directly proportional, which is very cool. So one little thing about the weight, it's kind of difficult to understand. I'll read it right out of the book. The upward force required while moving at a constant velocity is equal to the weight, or mg, of the object. So basically what that means is if I lifted this boulder up from this point to that point and I had a constant force, I did 200 joules of work. That's then considered the weight, okay? So since it says here, the upward force required while moving, so it's joules wouldn't be to measure the weight, of course, because joules isn't a measurement of weight, it's a measurement of energy. What we'd measure in weight would be newtons. For newtons would be our weight, because that's our force. Newtons are force and weight, because they're the same thing, right? Really, they are the same thing. So force or weight. So you'd find the force needed to lift that boulder up 2 meters, right? You go back to our work equation, work equals force times distance. So we'd have 200 equals F times 2. We'd get divide by 2, the force is equal to 100 newtons, right? Force is 100 newtons. Then you plug 100 newtons down in for mg, and then height would be 2, right? So that's how you're going to find the force or the weight. Force being the same thing as the weight. Newtons. Newtons is very cool. The unit newtons is very, very cool to me because it does both weight and force, and they're basically the same thing. So I think potential energy is pretty easy. The equation's very simple and it's pretty easy to grasp. It's just potential energy, the ability that some object has to give off energy, and it enables an object to do work, right? So let's move on to kinetic energy. This video is going to be a little bit longer than normal, but it's pretty important, so it's okay. Kinetic. Like I said, kin being movement or heat. And so we go on movement, right? Movement. That's kind of it's supposed to be a star. Okay, so let's look at movement. Okay, there's a little bit more of a complicated equation for movement, and for moving energy, I'm just gonna write that right off the bat. Ke, or kinetic energy, Ke is equal to 1/2 times the quantity of mass times speed squared, okay? It's a little, if you don't know your order of operations too well, or you might get confused on how to distribute out the 1/2 and when to multiply and anything, if that's often a problem for you, I recommend writing it like this, is equal to Ke is equal to mass times speed squared over 2. Okay, that's how I recommend writing it. It's a little easier. And then again, you're always going to want to square whatever the speed is before you multiply it by the mass. So let's just run a little problem. If the mass of something moving, let's say an arrow was shot out of a bow, and it had a mass of 2 grams, and it was going at a speed of 2 meters per second. Okay, it's a very strange arrow, but that's how it works. Let's find out its kinetic energy. Ke is equal to the mass 2 times the speed squared, so 2 squared over 2, right? So then we're going to do some algebra. 2 times 4 over 2, or that equals, I like to do little cancel out of the 2's, and then you just are left with 4. Kinetic energy is 4. Remember, we measure it in joules. Okay, and then there's an equation for the net force that you can find for kinetic energy, which would simply be it's very easy. It's just like the equation for work. Net force means all forces acting on an object times distance is equal to kinetic energy. Okay, just like work. Net force meaning all the forces acting on an object. So that's about it for energy, you'll see down there the work energy theorem, which is simply states that work is equal to the change in energy. So anything that has the ability to do work changes energy, right? So that's very interesting. And sorry that was a little rushed. It was a long video, a lot of sections to cover. But we'll move on to 8.7, or sorry, 8.6 and 8.7. All about, we'll start with conservation of energy, which then is very applicable to machines and how we make things easier for ourselves and efficiency and whatnot. So I'll see you in a little bit.